Hello, everyone. I think we're going to go ahead and get started. Thanks for joining today. Today, we're going to talk about lots of video delivery protocols, but primarily the internet delivery protocols. Just going to go here. There we go. This is the second of our webinar series here. Yesterday, there was Aaron did one on BISCA, kind of the technology there, some of the products that Sencore offers for that. As I said, today we're going to do the internet delivery protocols, kind of look at a number of different ones that are out there. There's dozens of them out there anymore, but we're going to focus on some of the more popular ones. And then tomorrow, Seth is going to do one on ATSC 3.0, kind of the technology there, as well as how Sencore is helping out in the deployment of ATSC 3.0. So a little introduction. I'm Jason Dabbert. I'm an account manager here at Sencore. I also do some product management and a number of different things, but hence the reason I'm here today. I also have Seth Vermolm and Aaron Doughton with me. They're going to be helping out, answer questions and things like that. They're both product managers here at Sencore as well. So we have our contact information on there. If anything comes up either after the webinar or during it, feel free to reach out to us, either in the Q&A panel there or anything after the webinar. You can send us emails directly and we can get back to you as well. So we'll go ahead and jump in here, the agenda. So we're going to do a brief history first on content distribution, kind of how we've done it in the past, kind of where we're going and where all those fit throughout the distribution chain. Then we're going to dive in a little bit on what's unique about video delivery versus just delivering data over the internet or over IP networks. What makes video unique, and what are the challenges that are associated with that, and kind of what solutions we have in place to deal with those unique challenges. And then the third one, where we'll spend most time, is why should we change? We've been doing video distribution for a long time already. Why should we change to IP or internet specific delivery? What are the advantages of that? What does it gain us? Things like that. So we'll go ahead and jump in here to a history. So as I mentioned, we've been doing this for a long time now, since the advent of television, basically. But we went from carrying around tapes like I've shown there to distributing it like that, physically carrying them from place to place, or even the old reel tapes, to more recent technologies like microwaves, point-to-point links, things like that, satellite. So whether that's either a microwave or satellite truck for local news gathering, or a DSS type of a service, where we take and send all of our content up to the satellite and then satellite down to the consumer. Terrestrial broadcast, there's many flavors of that, whether it's 8VSB here in the States or FDM or the other modulation schemes that are out there. But that's another very popular way to deliver content, both to your subscribers as well as the end consumers. ATM, I'm sure a lot of you remember that. Up until, I don't know, probably 10, 15 years ago, that was the primary way of distributing backhaul content from location to location. We did ASI and a number of different technologies over that technology. And then the final one there is dark fiber. So there's lots of, like, as we moved into IP delivery, things like that, we're looking for more ways to deliver that content over long distances very reliably, and fiber seemed to be a great solution for that. And that kind of segues into what we're going to talk about today here. So where are we going? As I mentioned, we've been doing it for a long time. A lot of those technologies are still out there and still in use today. And there's lots of reasons for that. Most of them are all very reliable technologies. And in a lot of applications, you need multiple different technologies in order to deliver the content to your end users. And for example, like we're going to talk about today with internet delivery, for the most part, internet is everywhere at this point. But there's still lots of applications where there isn't an internet connection, and you maybe need to do a microwave back to the studio or do a satellite backhaul or uplink from whatever event you're at. So a lot of those things are still in play today, and it's really not a one-size-fits-all solution when you're talking about content distribution or contribution. So you have to use a number of different technologies, and that's kind of where we're going to talk about the most today with these internet delivery protocols, is that, again, I think in most cases, you're not going to use just one of these protocols. You're going to use it in combination with one of the other ways that we've has been well established for content distribution. So some of the things we're going to talk about today with open internet-based delivery. So the top three there, it's Zixi, RIST, and SRT. Those are kind of the ones that we think about traditionally when we talk about content distribution and contribution, mainly to your subscribers or content aggregators, things like that. Now, the last ones, when we talk about HLS, low latency HLS, things like that, those are more geared towards consumer consumption. So right directly to the customer who's going to consume that content. We would typically use technologies like that. Now, there's lots of carryover and gray area and people using them for different things. So again, it's not a hard and fast rule that you're going to use certain technologies for certain applications. There's lots of places where these fit, maybe where they weren't originally intended or envisioned, but they work well there as well. So let's jump in to some of the unique challenges that we face when we're delivering video specifically over IP connections or over the open internet. So the real-time nature of it is probably the biggest hurdle that we run into. When you think about all other data delivery, internet surfing, all that type of stuff, it relies heavily on re-requesting of packets, acknowledging of those packets, all those types of things, and then resending stuff that maybe didn't make it to its destination or arrived errored or things like that. But when we have video, it kind of has to all be there now. Otherwise, you don't have any time to go re-request the packet before that time in the video has passed, without the use of huge buffers and delays and things like that we'll talk about here as we go forward. So that's really the biggest thing there, is that you just don't have the time because of the real-time nature of it. The second one is compression. So video is a massive amount of data in its raw, uncompressed form, as we know. And moving that type of data around, while we've made some strides in that direction, it's still not very economically feasible to distribute it to the end customer that way. So we have to compress it all. And the whole reason behind compressing, or the whole nature behind compressing, is that we're removing most of the data there and trying to trick your brain into thinking that all of the data is still there. And the most common ways we do this is by not sending all of the data with every single frame of video. So we have our key anchor frames, our iframes, and then we have Bs and Ps that play off of those that fill in the gaps. Well, if we miss an iframe, for example, a packet that's carrying an iframe, then we get lingering artifacts for a certain amount of time after that, and not just on that single IP packet. So it's more important than ever to be able to get all of the data there cleanly and error-free, so you don't end up with lingering artifacts in your video long after that single packet has been dropped. So that makes it very important to be able to reliably deliver your video across these mediums. And then the last one is buffering. And we're not talking about the buffering that you see when you're streaming and the little spinny wheel comes up. We're talking about the buffering both on the sender and receiver side, so that we do have a chance of recovering packets, reordering packets, maybe getting a chance to re-request a packet. But all of that buffering comes at the cost of latency. And when we're watching things that are inherently live, like sports and things like that, you don't want a 30-second or minute delay, because I think many of us have experienced where maybe one of our neighbors is watching the game on satellite and you're watching it maybe on the local off air, and you start cheering when there's a touchdown or something like that, and then a minute later the people on satellite start cheering. No one likes to be left out like that. So they want to get it right as the action is happening. So we want to minimize the buffering as much as possible, but we do need it in order to make sure that we can get a reliable stream to you. So how have we dealt with these things in the past? We've had a number of different solutions that have come across as standards or recommendations that help us deal with this. And I've listed a few of them here. And the first one is the forward error correction. So SMPTE standardized this into 2022-1 forward error correction. But basically what this does is that you define a matrix of packets, and the size of that matrix dictates both the overhead that you're adding to the stream, as well as the amount of recovery that you'll be able to do. So and it's kind of counterintuitive. So the smaller the matrix, the more overhead you have, and the more recovery you can do. But in the larger matrix is the less amount of overhead and less amount of recovery you can do. So that, I guess, is kind of counterintuitive when you just think about it at face value, but when you get down to look at it on paper and kind of how it pans out, that's the way it works. But basically, the way this works is that the FEC packets are organized into rows and columns, and those FEC packets contain just partial bits of the actual IP packets with the video and audio in it. And the idea there is that any FEC packet can correct any one of those packets inside the matrix. So that's kind of what I'm showing there on the right-hand side. But the biggest thing the biggest 2 points to take away from this one is one, it can add a significant amount of overhead, and I'm talking like 25% overhead or more. And secondly, this solution doesn't really work well for internet delivery. So you can see in this type of solution, it's best suited to correct sporadic packet loss. So maybe 1 or 2 packets here and there. But what we see in internet delivery is that you end up with large chunks of packet loss or large chunks of delayed packets, which is what I'm going to talk about here in a little bit. But even if they're delayed, they're as good as lost because of the real-time nature of video. So it works well on private networks. And some basic internet connections, it'll work decently well, but for the most part, you're still going to end up with lost packets and ultimately degradation of your video and your audio. So you'll see as we talk about some of these protocols, this is still heavily used, just not by itself in combination with other technologies. A very simple one here is the RTP sequence counters, which is what FEC builds on top of, but this is just numbering packets as they leave the sender, and then the receiver gets those packets, looks at the numbers, and figures out which packets go in what order. So if they arrive out of order, we can quickly flip them around and feed them to our receiving device in the correct sequential order. So we talked about buffering quite a bit there, and we'll talk about it in more detail as we go. So I'm going to leave that one. And then the last one is automatic repeat re-request. And this is just a way of the receiving device acknowledging, or in this case, negatively acknowledging that they didn't receive a packet or received a packet that was errored, and asking the sender to send it again. And you'll see a combination of all of these things in the technologies and protocols that we're going to talk about here in a little bit. But any one of them on their own does not do well for internet delivery. So why don't they work? I touched on this a bit, but the biggest thing that I was going to mention here is that all the packets that are technically lost aren't actually lost in a lot of these cases. They end up being delayed in one of the routers or switches between the sending device and the receiving device. And like I mentioned, if they're delayed, they're basically as good as lost unless you have a very large buffer, which adds a lot of latency to your stream. So that's one of the other big challenges there with the IP or internet-based delivery is you can't, even if the packets arrive ultimately error-free, if they didn't arrive in time, they do you no good. So why should we change? Outside of the problems that we talked about previously here, there's lots of reasons why we want to continue to move forward. Technology changes, cost changes, all those types of things. So it really is advantageous for us to look forward at these technologies. How can we utilize them in our workflows? How can we change or supplement our workflows to use these things and to keep a leg up, not only on the competition with delivery mechanisms, but in content acquisition and just the economics of getting that content onto your distribution network. So I touched on it, but the biggest thing is cost. We're always looking for ways to decrease the cost of our content distribution and contribution. Dark fiber is expensive, doing microwave links is expensive, deploying satellite trucks, very expensive. Most of these venues and places where you're going to be getting content anymore has an internet connection. And especially in the last 10 years, internet connection speeds have really drastically increased, which makes it very economical to deliver your content over the internet now. If a 10 meg connection was $1,000 a month 10 years ago, and today you can get multiple gigabit connection for that same price, it now makes a lot more sense to deliver all your content that way. And the second point here is the ease of deployment. With a lot of these technologies, it's very, very quick to get your feed up and running and be backhauling your content in a matter of minutes. Whereas previously you would send people out days in advance or weeks in advance to set up these links, test them, validate that everything was working well long before the actual event happened or you needed to actually backhaul your content. Or say you had to wait for construction of a fiber circuit or something like that, that takes months. So that's really the big advantage here as well. So if we have a small event that's only going to last a couple of hours, if I can use one of these internet delivery protocols, I can literally show up on site, plug into the internet, plug my camera in, and I'm up and running. So it just takes a couple of minutes. And that's a really big advantage as far as personnel costs and getting everything up and running and proving that out. So you can see kind of they both play on one another, but ultimately cost is the king here. And we see that day in and day out in the industry. So let's talk about the new kids on the block. And you'll see here a few of these. Really the advent of internet, or the idea of delivering content over the internet, really started about 10 years ago. And when this first came about, Zixi and VideoFlow and LTN, there's a number of people out there that are doing this and have been working on this for the last 10 years. But right when they first came out, you heard the snickering in the side wings of conversations, people talking about actually delivering stuff over the internet and how that'll never work and they'd never trust it and things like that. And then a few people tried it and it seemed to work all right, but they still reserved it for their backup feeds. They'd still do their primary feed over satellite or over fiber or something like that. And they'd maybe fire up a VideoFlow or Zixi feed on the side just as a low-cost backup feed. But really in the last, I'd say 3 or 4 years, people have widely accepted that this is a very reliable mechanism to deliver their content and have really moved more towards the direction of using these internet delivery protocols as their primary means of distribution. So it's taken a long time to get there. Just like any technology, it has to be proven out and gain acceptance from the industry and the consumers. But I think we're really there now. And I've narrowed this presentation down just to a few of the technologies. Like I said, there's lots of them out there, but we'll just touch on a few of them here. But as I mentioned, Zixi came to market about 10 years ago. They originally started by selling appliances that did all of this. So they would have a feeder appliance that was a little computer piece. They'd have a broadcaster appliance, and they'd have the receiver appliance. And all of those were just meant to take in a normal transport stream, put the Zixi proprietary protocol on top of this, distribute it, and then strip it off at the other end and bring it back down to a traditional MPEG over IP transport stream. Now, kind of as we've gone, kind of as they've evolved as a company, they've moved more towards a software-based approach and having vendors integrate their technology into their products to both simplify the workflow and simplify their distribution model there. So video flow, very similar thing with them. I think they do still sell quite a few appliances. They've been a longtime Sencore partner along with Zixi in both, and we've been working with a lot of these guys to enable their technology by selling our decoders and gateways and those types of things that really help move these flows around. The last one or second to last one here, I guess, is SRT. So this was developed by Haivision and Wowza, and then open sourced in 2017. And that it really has a huge number of contributors since going open source. There's, I think, a couple hundred contributors now to this Git project. And it's really seen a big surge in acceptance and integration into a lot of different products. So the really nice thing that a lot of people gravitated towards SRT was A, that it was open source, and B, that it was free. With proprietary protocols like Zixi and VideoFlow, you have to pay per use or different pay per models there. Whereas SRT and then RIST that we're going to talk about are both free to use. And that leads us into RIST. So this was developed by the VSF, and they took a different approach. Instead of like Zixi and VideoFlow that are proprietary approaches, SRT, which is kind of a proprietary approach that was open sourced, RIST took a different approach that they were just going to look at existing standards that are out there and build a new specification around existing standards. And if you've been in the video industry for any amount of time, you know, basically all of us love our standards and prefer to have every product built around an open standard that allows very well or very good interoperability between all of the products within the industry. It just makes it very easy. So some other internet technologies I want to touch on quick here. Again, these are more, the first couple, I guess, are more geared towards delivering to the end consumer of the content, which is HLS, HTTP live streaming. I'm sure most of us have heard of that one. Developed by Apple primarily for over-the-top streaming, again, to end user devices. More recently, Apple's released a low latency variant of HLS, which adds on to their HLS standard, but adds a number of different mechanisms in there to decrease the inherent latency that HLS has in it. The next one is a protocol that's been around forever, and we're going to touch on it here later, but many of us wish it would die, but real-time messaging protocol. It still gets a lot of use because it is low latency, and it works well over the internet. It was developed to be over the internet since its inception. So it's still heavily used. There are a lot of other technologies that are up and coming and that are more widely accepted that have even lower latency. So I'll touch on why we'll see this one probably fading out here in the years to come in a little bit. And then the last one here is the real-time streaming protocol. Again, this was developed by Real Networks, but it's mostly for commanding multimedia content. So your play and stop and fast forward and all those on your video players on the internet. But it is used heavily throughout a lot of these other protocols as an underlying protocol to enable them. So before we jump into these protocols specifically, think we have a couple questions here.
Yeah, there was one of the questions from the audience, and I think it was when you were talking about a lot of the different recovery mechanisms and stuff like that. And there was a question about how can SMPTE 2022-7 be used in some of these protocols, or does it even really apply to these different protocols?
That is a pretty good question. So I don't think, well, none of these protocols implement it in their underlying level, but it absolutely is a good mechanism for error recovery over the internet as well. The biggest problem with 2022-7 is you have to have double the bandwidth then because you're sending the same stream twice. So that would probably be the biggest drawback there, especially if you're bandwidth limited. Again, most places are not nowadays, but there are still plenty of places where you're going to run into bandwidth constraints. But yeah, 2022-7, again, all part of that 2022 SMPTE standard is a very good supplement, I guess, to add into the suite of error recovery mechanisms that we talk about when we talk about internet delivery. So, all right, so let's jump into a few of these technologies specifically here and do a little bit deeper dive. I only have a couple slides on each one of these just for the sake of time, but just know that basically any one of these technologies I'm talking about today, we could do an hour-long presentation on that single technology itself. So we're going to stay pretty high level, stick to the points that are the most important to remember, and then move on. And there, like I said, there's plenty of other information that we could talk about on these, but we just don't have the time today. So the first one we're going to talk about is XIXI. So proprietary protocol focused on reliable video contribution and distribution across the open internet. This has been their goal since the very inception. And like I mentioned, we've been working with them since the beginning of them being a company. So we used our decoders to help enable their technology, mostly on the back end. So after they would strip the XIXI back off, our decoder would receive that MPEG over IP stream and do the decoding. They're very widely known industry leader in this field. I think you'd be hard pressed to find anyone in the broadcast industry that hasn't heard of XIXI before, and they're widely accepted. The protocol seems to work. It does a great job of delivering over the internet, and the big piece, or the big advantage, I guess, in my opinion, of the XIXI protocol is their Zen master. Which is what most of their technology is built around now, which is kind of like their grand central station of all the XIXI feeds, and does all the orchestration of not only the feeds, but you can also put in all of your products into XIXI Zen Master, which then acts as like a remote NMS to your products that are out at the edges of your network. So you can put the products in there, you can command your products, you can change the inputs, outputs, everything you would do on a lot of the web GUIs right from that XIXI Zen Master. And then you can watch the streams come in, you can monitor them for health with your traditional TR-101-290, and then either send it out to a single destination or multiple destinations. And that's the other thing I wanted to point out on these slides is that I put a little icon up in the upper right-hand corner there delineating whether the protocol is focused more around point-to-point contribution distribution or point to multi-point. And you could make an argument for most of these that at the core of them, they're all point to point, but certain ones make it easier to do a point to multi-point distribution than others. So keep that in mind, but I wanted to make that point so that you can see the differentiation as we talk through these here. So continuing on with XIXI, it's an app. The core of it is an application protocol on the top, riding on UDP with both proprietary FEC and standards-based FEC. They have DTLS and AES encryption built in, so you can use any of those. They have means of doing low latency down to as low as 300 milliseconds. And with any of these protocols, you have to remember that your trade-off of latency versus reliability always go hand in hand with one another. So as your latency increases, so does your reliability, and the vice versa there. As you decrease your latency or your buffering, your reliability goes down as well. So like I mentioned, proprietary FEC as well as 2022-1, and they add some proprietary ARQ in there as well. So not a whole lot to be talked about with how their technology works. Obviously, it's proprietary, so not a lot is made public on a lot of that stuff, but these are a few of the key points there. I put a note in there about supporting most other internet delivery protocols. So really in the last few years, XIXI has made a push to be able to ingest basically any of the other internet delivery protocols. So this would be talking about on their Zen Master side. So the Zen Master doesn't just have to receive a XIXI feed. It can receive an SRT or a RIST or many of the other ones out there, even HLS. So they can ingest a lot of these other protocols into their ecosystem and then distribute out from there with their XIXI protocol as well. So like I mentioned, they originally sold it as hardware pieces. Those 3 pieces are still pertinent as far as how the delivery chain works. You have a feeder that's going to originate the feed and send that into the Zixi ecosystem, which would ultimately, in most cases, end up at a broadcaster, but could also end up straight at a receiver, and that would be your point-to-point connection. But for the most part, it pretty much always goes to a broadcaster for a number of reasons. And then the last point here is that the feeds can either be pushed or pulled. So you can either push feeds up to a broadcaster or push them straight to a receiver, or they can be pulled from the broadcaster by a receiver itself. So a receiver can say, I want this feed from this broadcaster, and pull it down from the broadcaster versus the broadcasters initiating the connection there. And then you'll see this point with traversing firewalls is a big important piece when you're getting, when you're moving feeds from corporate networks out onto the public internet and then back onto corporate networks again. There's nearly always a firewall in place. And it's really a pain to go to your IT department and say, I need these ports open for this reason and for these IP addresses. And then you're ultimately met with 1,000 other questions from your IT department and other restrictions that they want to put on you. So it's easier just to use a protocol that will traverse firewalls without any specific configuration. So that's kind of what we're talking about here. And most of these protocols that we'll talk about will traverse firewalls by using a feature in firewalls called connection tracking, which basically says, if I'm inside the corporate network and I talk out to the internet should be able to talk back to me on that specific connection. So that's what a lot of these protocols will use. So you'll see on my diagram on the right there that if I have a sending device, say a Zixi broadcaster that's trying to send to me inside my corporate network, it will nearly always get blocked on the edge of my firewall because it's an unknown connection trying to access the corporate network. Versus if I have my receiving device inside the corporate network and I talk out to the Zixi broadcaster, then the Zixi broadcaster knows to talk back to me on that same port, and it will automatically traverse the firewall, and my feed will, and my connection will be established, and I'll get the feed successfully. So you'll see a lot of that used in a number of these protocols, and it works very well. And then the last thing I wanted to mention on Zixi is just the pay-per-use model. That is an important distinguishing factor here when you're talking about Zixi versus a lot of these other protocols that are just free to use if you implement the standard. So moving on to SRT, this one is a bit interesting. Like I mentioned, it's mostly a proprietary protocol that was put into the public domain and open sourced in 2017. The reason I say it's interesting is there's been a lot of talk in the last couple of years since it has gone open sourced that Haivision has continued to develop and iterate on this protocol internally and not necessarily contributed it back to the open source project, which has led to a lot of incompatibility between Haivision SRT and the SRT that was open sourced. So I don't know that you'll run into it a lot, but it's a thing to keep in mind when talking about SRT is when you see the word SRT, don't necessarily assume that all SRT is created equal. So I think a lot of the independent vendors, you'll see a lot of interoperability working just fine. I think where you'll see it is when you run into the Haivision specific stuff there. But the protocol itself was derived from UDT, which is kind of a mouthful when you're used to saying UDP. But really it's just derived from a data transfer protocol, moving data from one point to the other over UDP. The thing that SRT adds, a couple of things, it adds the connection and control tracking, as well as some native encryption support, so AES encryption support. And then the last point is that it uses periodic acknowledgements, and instead of acknowledging every single packet, it just acknowledges them periodically, and then utilizes immediate NACs or negative acknowledgements to get packets re-requested for ones that may have arrived late, not arrived at all, or arrived errored. So the important piece there with the re-requesting of packets that SRT uses is it utilizes burst transmission. So if there's a number of packets or a packet maybe that needs to be re-requested, it requests that from the sender, and then the sender sends it much faster than the normal rate of the stream that it's sending. So the idea there is that hopefully that packet that was missing can get to the receiving device much quicker than the normal stream, thus being able to utilize that packet, put it back into order with the packets that arrived before it, and be able to decode the video and audio cleanly on the other end of there. So important piece to keep in mind on SRT with that. So continuing on, some important pieces with SRT. I talked about the native encryption support. So it does support AES 128 and 256 encryption. And then the other thing to keep in mind here is that there are 3 modes that all of your SRT devices will end up being in, and you'll have to configure these devices in most cases to be in one of these modes. So in caller mode, this is a device that's calling out to the listener to try to establish a connection. And you have to have one device on one end as a caller and one as a listener on the other end. And this is just, again, setting up the connection to be able to send the stream through there. So if we think about the firewall application, again, kind of like I have depicted on the right-hand side there, if the caller is talking to the listener, say a caller is inside the corporate network, it's going to be able to get out, talk to the listener is going to be able to talk back. That will traverse the firewall just fine. But say the caller is outside of the firewall, it's not going to be able to get in and talk to the listener. So that mode won't work in that scenario there. So just an important piece to keep in mind. And then obviously the listener, this is the guy that's just waiting to be called by the caller. So he's sitting there, you have your stream set up on it, and he's just waiting for the caller to call and talk to him and set up that connection. The nice thing about the listener is you don't have to do much setup. You don't have to know who the caller is, any of that stuff. It just sits there and waits to be called upon. The caller knows the IP address of the listener and the port and all that stuff and handles all that for you. So the last one is rendezvous. And the important piece to know here is that in rendezvous mode, your sending and receiving devices both need to be in the same rendezvous mode. So there's no caller and listener anymore. Both devices are both acting as callers and listeners. So they're both reaching out to one another. They're both listening for one another. And again, just another way of easily traversing a firewall. And I would say this is probably the most common way that we've seen SRT implemented. I put a note at the bottom there, which is something that kind of messed with my mind for a while. It is an important piece to differentiate, is that any device, whether it's sending or receiving, can be any of these modes. So it's kind of intuitive that, so you would think that a caller is always your sending device and a listener is always your receiving device, but that's not necessarily the case. Either one can be either one. And like I said, when you first think about it, you're like, that doesn't make any sense. But as you understand more about how it's traversing the firewalls and how it's setting up this connection, it makes more sense on why that is the case. But again, important piece to remember there. So moving on to RIST, or the reliable internet stream transport. Oh, looks like I forgot a bracket at the end there. So after many, many years of proprietary based protocols to traverse the internet, the VSF finally came together and said they were going to create a more standards-based approach, which again, us people in the broadcast industry love our standards. So naturally, there was lots of interest in this approach. So this has most recently been finalized, the first couple of profiles that we'll talk about, and there's continuing work to evolve that. But again, it utilizes many current SMPTE standards along with a number of RFCs that are out there. It's built on UDP with RTP headers. And the reason that this is important is that it makes it backwards compatible with a lot of receiving devices that don't necessarily support RTP. It can just grab the UDP out of there and decode this like it is a normal MPEG over IP stream. But obviously, you're not going to get any of the error recovery or all the mechanisms that RIST was built for. But the stream is still inside of there in its natural form. The protocol itself is comprised of two profiles, and I put currently in there because there is ongoing work to expand this. A simple profile is your basic error recovery over the internet, and then main profile adds a lot of additional tools on top of that to make it more efficient, make it traverse firewalls better, things like that. So these two profiles, I'm going to dig in a little bit here in more detail, but I put on the right-hand side there kind of how the hierarchy of them. But we have the simple profile, and then each one of the ones, the main profile and enhanced profile, all build on top of those. So in the simple profile, again, we have our ARQ, retransmitting, link aggregation and bonding, redundant transmit path, things like that, that are going to just get a reliable stream across the internet. Then in main profile is where we really, I think, in my opinion, add a lot of useful features specifically to sending over the internet. So the big things there are tunneling, which gets us through the firewalls easy. In simple profile, we have to go talk to the IT department again. We don't like doing that. So it gets us around that. It adds multiplexing, so we can take multiple simple profile streams, mux them together, send them all over the same connection. The third one is a very important piece on why most people didn't use simple profiles, because it didn't have any encryption in it. The content that we're sending or distributing is very valuable content and requires encryption in nearly all instances, whether just to protect the content or by contractual obligations. So we have security now in there using DTLS. Multiple ciphers are supported as well. AES is in there by default, but any others can be added if those vendors want to add them. And then the final one is the bandwidth optimization. So the neat thing here is that in nearly every transport stream, we have a certain percentage of nulls in order to keep it a constant bitrate stream, set up our buffers appropriately when we're doing decoding, things like that. But those packets are just empty packets that are filling spaces in time. So when we're sending this over the internet, we don't need to waste the bandwidth to send those packets. What we can do now with RIST is we can just put a marker in, say, hey, a null packet or 6 null packets belongs here, so that the receiving device can then insert those back in and recreate the constant bitrate stream without wasting that bandwidth across your internet connection. So very useful features that were added in the main profile there. And I think with the addition of those, we'll start seeing a lot more adoption of RIST in the industry here. So continuing on, like I mentioned, this is a standards-based approach, utilizing primarily SMPTE standards and RFCs, which are internet-based standards and IP-based standards. So I highlighted 4 of the primary ones here. SMPTE 2022-2, which is just transport streams over IP, 2022-1 that we talked about previously, which is forward error correction. RFC 3550, which is the RTP protocol, which is the base of nearly all these standards that we're talking about, or protocols that we're talking about here. And then RFC 3605, which is a real-time control protocol, which adds a lot of the control and monitoring metrics to the RIST protocol. And then you'll see there's nearly a dozen other ones that are rolled up into the RIST protocol, RFCs and SMPTE standards, but these are what the core of it is based off of here.
I was going to address a couple of the questions actually that came from the audience.
Sure.
It's a kind of two-part question or two-part comment. One of the comments is, which one is better for link bonding? And then also Audio at Video Flow did point out that RIST actually does support link bonding and load sharing. But one of the things just I think for the audience is there any particular one that's better at link bonding versus the others or not?
I guess I'm not here to point out which is better than the others. Again, I know most of them support it and do it well. In my experience, I've seen them all do it well. I haven't necessarily been in situations where it's been extremely challenging, but I guess from a vendor standpoint that supports all of these, I guess I don't necessarily favor one versus the other. I think they all do a good job.
I think from an implementation standpoint, just being one of the product managers here at Sencore, this is Aaron. One of the things that we've seen, some of the documentation, or at least the libraries, in order to adopt some of these protocols like RIST or Zixi or VideoFlow or something like that, they do a much better job of describing to vendors how to actually implement link bonding. And I think that's really important. Any of these protocols could technically do link bonding or load sharing, but you might have to come up with that mechanism yourself, where this is, much better. It's easier to do, I guess, from a vendor standpoint.
It's like making the engineer's life a little easier.
Yeah, maybe, exactly. I really think that's a lot of it. So.
But from an end user, I think they all do a great job.
Mm-hmm.
Is there another question?
Let's see. What does the maximum bitrate do protocol support?
I know there's some bitrate limitations on these. I don't have them off the top of my head, but I think for the most part, as long as your internet connection is going to support it, that's going to be the biggest hurdle here versus the actual protocol itself. So as long as your internet connection has the bandwidth to support it and the latency to support it would be the other thing. Then I think you'll be fine with most bit rates.
It looks like SRT may be limited to 30 megabits, and RIST does not have a specific limit.
Well, I know there's an effort here with RIST, especially to add a higher bit rate support, but I don't know what the exact numbers are off the top of my head. So.
Right.
Well, like I said, we can spend a day on any one of these, talking about them in depth and getting into the weeds, but I want to continue moving here. I know we have a short amount of time, and I want to honor everyone's time here. So let me finish up with RIST here and a couple more. I think we have a handful more slides, and then we can get to more questions, I think. So. Continuing on with RIST here, we talked about the RTCP doing the reporting and the control piece of this, but it does a number of different things in the RIST protocol. It does the lost packet counting. So between the sender and receiving device, there's lots of reporting metrics, health metrics, those types of things that are exchanged, so you can pay attention to the jitter on my connection, how much bandwidth is available on the connection, how my packets are arriving, how many packets I'm correcting, not correcting, all those types of things. And the RTCP protocol is responsible for all of that. And continuing on here, the NAC requests are also carried in these RTCP packets. And you can see on the right-hand side there, if a packet wasn't received, the receiving device is going to send that NAC back to the sender, asking to resend that packet. And the couple of buffers that are shown there are important. On the encode side, we can have huge buffers and keep packets for long amounts of time without negatively impacting the latency of the overall stream. Really, the only thing that's limiting us there is the amount of storage space available at the encoder or whatever is generating the stream. But on the decoder side, the larger the buffer that you create, like I mentioned earlier, the longer the latency you're going to end up with, but also the more packets you're going to be able to recover. So if latency isn't a concern and just getting a pristine stream is more what you're looking for, then obviously increase your buffer size, and you have a better chance of recovering every one of those packets. And you can see in that example there, I got the packet retransmission, but maybe my packet retransmission that came to me, maybe that was errored as well. So with RIST, I can re-request the same packet again, basically for as many times as I want, within the bounds of the buffer on the receive device. If we get outside of that buffer, we may get the packet outside of the time when it's useful. and then we might as well have not received it at all again, like we talked about. So, and then the last point here was just what we talked about, but the buffers on both the sending and receiving devices are configurable, and how you set these dictates how fault tolerant or latent your stream or your transmission is, or the vice versa of that. So moving on to a couple of others that I wanted to just touch on here briefly. We're not going to go into too much depth, but HLS, like I mentioned, I think everyone's familiar with this one, but developed by Apple, primarily used for delivering video to end users or end consumers of the content. It's supported by everything Apple makes, as well as pretty much every consumer device out there at this point, including all your Androids and Samsungs and all the other brands out there. Pretty much everything supports HLS. It's extremely reliable and fault tolerant, but as we mentioned, the fault tolerance comes with a cost, which is usually latency. And HLS is inherently known as being a very latent protocol, but again, very reliable. So in the early days of HLS, you would typically see about 30 seconds of latency in these transmissions, which is huge in a lot of the live real-time video that we're talking about today. So it didn't lend itself very well to primary video distribution. Now, as the technology has evolved and things have matured, that latency is not necessarily 30 seconds anymore. A lot of the times it's less than that. But the protocol works by just taking a traditional transport stream for the most case. Obviously, there's edge cases to a lot of this, but for the most part, it takes a transport stream, it chops it up into little tiny pieces, anywhere between 2 and 10 seconds traditionally, but this is configurable to whatever you want, and sends those transport streams a little bit at a time. And with any over-the-top streaming protocol, you're going to have multiple versions of the exact same stream at varying qualities, bit rates, frame rates, etc. And this just makes it a nice seamless experience to the end user to be able to receive the video regardless of what their bandwidth is. Obviously, it's not going to be as good a quality if you have very low bandwidth as if you have a really high bandwidth connection, but you're still going to get the video. It's not going to buffer, and it's going to be a pretty seamless experience to the customer, which is what you're ultimately looking for with your over-the-top streaming. So we're going to take these chunks, we're going to chop it up, we're going to list all of these inside of playlists, and then the player on the client device is going to analyze the bandwidth that's available to that particular client and ask for the specific chunks that it thinks it can support on that connection. So we have a top-level playlist. So when the client first reaches out and wants to receive the stream, it's going to request the top-level playlist. That playlist says, all right, I have 8 different versions of this stream. They're anywhere from 4K down to 240 pixels. And they're this bit rates. They have these audios, this frame rates, etc. Which one do you want? The player will read that and say, all right, based on this client is on a great internet connection, I think I can support the top level one. And it's going to read the next level manifest then for that top level playlist. Reads that playlist file, and inside of that playlist file is just a bunch of links for all these transport stream chunks. So once it receives the name of these chunks, it can then reach out directly to the CDN, say, give me this file. And that's no different than if you were trying to download a file from a website. It's doing the exact same thing, except for in this case, it's a small transport stream file. It grabs that chunk, puts it into the player decodes it, presents it to the user. And that process continues on and on and on, just downloading individual files over and over and over again to create the entire show or live broadcast or whatever you're presenting there. So, and the manifest files are continuously updated. This is an important piece as we go forward here. So I talked about a little bit about that. AES 128 is natively supported here. As you'll see in a lot of these, the encryption piece is very important. It traverses firewalls without any issue because it's based on normal HTTP traffic, which firewalls are used to passing. So just like you're browsing the internet, it's going to look no different here in this case when you're streaming the video. So we have seen some gaining popularity as a distribution method using HLS. So I think 2 slides ago, I just mentioned that it's not really used for primary distribution. But what we've been seeing is that because of its error resiliency and ease of implementation, we've seen a lot of people start using HLS for primary distribution because of those reasons. And I think there's a lot of factors that go into this. Obviously, I don't think you're going to be using HLS for your primary distribution on live breaking news, things like that. But maybe if you're just streaming out like VOD content or something like that, could be a lot of different applications where you would use it, where latency doesn't necessarily matter, but error-free delivery is your primary goal. We've seen HLS being used there. So we've had some push from customers to implement that into our receiver decoders and things like that. So we've been looking at adding those into the gateways and receivers in order to help our customers out in these applications. So we talked about HLS being a very latent protocol, having lots of latency, but high error resiliency. And that's been great, but as we get more of these, as the broadcasters are pushing more towards getting the latency down, Apple has heard those calls, and in 2019 at the Worldwide Developer Conference, they came out with a low latency, basically extension to the HLS protocol that adds a number of different things in here to help keep the latency low, keep the interactions between the end user devices and CDNs to a minimum, and decrease the amount of content or the amount of data that needs to be transferred between both of those. So with low latency HLS, here again, we take our chunks, but we chop them into even smaller sub chunks. So this does 2 things. One, it allows us to start a stream quicker. So once the player requests a stream, it can request one of the first parts. So if it's partway through one of the chunks in normal playback, I can now request a partial of that chunk and start my playback right away instead of waiting till the next boundary point or next chunk is available on the CDN. So quicker starting and being able to start at different points within the stream. The second piece that low latency HLS adds is allows the clients to request segments that aren't yet created. So this is important because the client can now reach out and say, I want this stream when it becomes available, and cuts down on one of the back and forths between the either the CDN or the origin server. And now when that part becomes available, it's automatically pushed to the client, and the client doesn't have to re-request those. And that kind of goes along with the next point here, is it introduces a push mechanism as well, which allows the client to say, hey, I want this file, but it also sends the manifest file up along with that. So when I mentioned that the playlist files are continuously updated, normally you would have to go out, get the new playlist file, read that, request the new chunk, get that back. And you can see that's a number of different back and forths with the CDN, not only with the amount of traffic, but just with the sheer volume of packets that are being transferred there. So this way it allows them to send that all in one request. So I can just say, hey, I want a manifest update and send me the next chunk that goes along with that. So we get the amount of traffic between the player and the CDN is basically decreased to half of what it normally would be. The next important point with the profiles always being, or playlist continuously being updated, is that we've now added Delta manifest updates. So before, what you would get is a manifest file that said, all right, I have these 10 chunks available for you. When I go get the next manifest file, it says I have these chunks available for you minus the one you just used. So you're resending a lot of redundant data over and over and over again. And what the Delta manifest updates allow you to do is A, get smaller updates without the redundant data, and B, in most cases, get all of those in a single IP packet inside of a single MTU. So 1,500 bytes there. And it just makes the exchange that much quicker again. So because I don't have to send that much data. So another important piece there. And then the final one there is the rendition reports, which gets information about other versions of the stream that may be available. So I can say, hey, I want this stream and I want this chunk, but hey, also give me information about these other streams that you may have. So it can do that all again with less requests back to the CDN. And that's really the focus around most of the tools in low latency HLS here, is just cutting down the amount of interaction I have to have between the client and the server. And to finish up with low latency HLS, again, we're working on getting the latencies down. So in most cases, you can get down to 2 seconds of latency or less compared to your typical 18 to 30 seconds of latency with conventional HLS. So you can see drastic improvement there. And there are lots of other technologies, like I mentioned, that are getting latencies down as well. So this is just another important tool in your toolbox when you're looking at delivering over the open internet. The other big caveat here, which was recently changed that I mentioned here, but in the original low latency HLS specification that Apple came out with, they required HTTP2 to be implemented all the way through the signal path in order to support push. So if you remember from the last slide there, if I'm requesting my manifest and chunk, it's going to send all of that in a single request. But in order to do that, it needed everything in the signal path needed to support HTTP2. And in the latest rendition here that Apple released, you no longer need HTTP2 to be supported at the CDN level, but it still needs to be supported at the end user devices in order to do this. So just an important caveat there. And this standard, along with a lot of these others, will continue to evolve as we go here. There's been lots of progress here, like I mentioned, in the last 10 years. I think the last one I wanted to give a nod to is our old friend RTMP here. And I do mean old. You can see this was developed back in 1996 to deliver Flash content across the internet. As you know, Flash has been basically phased out of the internet for a number of years at this point. And the RTMP protocol has really kind of been repurposed for low latency video delivery, just because A, it's low latency, and B, it just works. At its core, it was meant to deliver video over the internet. So it was designed all the way around that from its very inception. So I mentioned there, it's still widely used to a lot of people's begrudgingness. But I think we will see it here as these other profiles have gotten their latencies down. I think you'll see that RTMP will continue to fade into the woodwork along with its ancestor there, the Flash protocol. But the biggest thing here is that with RTMP protocol, it is a client and server direct connection handshake that needs to happen before anything can happen or before any data can be transferred. So that's just what I depicted over on the right-hand side there, is the initial handshake that has to happen directly between the client and server in order to start the transmission. And then the last thing I noted there is that that they have announced end of support completely for RTMP in 2020. That's not to say someone else won't pick up support for it, but let's all hope that it continues to go by the wayside and we can use some of these newer, more flexible protocols to deliver over the internet. And that's all. Like I mentioned, we had to stay pretty high level on a lot of these in order to stay within the time. But hope you were able to learn something there. I did just launch the poll there. If you want to go ahead and fill out the poll and any follow-up that you'd like us to do with you, or if you want to just get a copy of the presentation, let us know. Also, if there's any other questions, we'll take those now. I'm getting some nodding heads that there's no more questions. So I want to thank you all for joining this afternoon or morning or evening or whatever time it is in your part of the world. And be sure to tune in tomorrow for Seth's presentation on ATSC 3.0. Thanks, everyone.